Today we're going to talk about our first section that we read yesterday regarding the science of physics. What is physics? Why are we studying it? Why do we care anything about it? Our goals for listening to this recording, we want to understand what the science of physics involves. Once again, why are we studying this? Why is this part of science? We also would have, if we had the equipment, we would have interpreted motion graphs. We will come back to this objective, so don't worry about that for now. We have discussed some of these, or you have read about some of these vocabulary words, but these are vocab words for our unit here. You will definitely need to know all of them. Because they're different sections that we are going to be studying throughout the entire year. So pause for a moment, and before we even begin taking notes, I would like for you to pause and fill in what you believe the answer to be for number 2 and number 3. The terms that we're going to work with, you've already seen. Specifically, I would like to focus on position over the next couple of days. We're going to mostly look at position here, but eventually we'll get into velocity, which should be really familiar to you. This is the vector quantity of speed. Acceleration, if you guys drive, you know what acceleration is. Force, work, and energy. And when we talk about work, we're talking about the physics term work. So just something to be mindful of, because it can be a little confusing that these words mean multiple things. So whenever we're talking about these words, we're talking about the physics definition of them, the actual scientific definition of these words. So what is physics? Physics is the science that explains how the physical universe works, so how things around us are interacting with one another. Why do things fall to Earth? Why, if I push something, why does it move? Okay? So an example of this is Newton's law can be used to describe the motion of the skydiver. Because you jumped out of a plane, you are going to fall to the center of the Earth because of gravity. Okay? And because of gravity pulling you at a certain force, you have velocity, you have acceleration, you also have forces acting on you. So everything that we see and everything that we do in the natural world, we can apply physics to that. So why did you take this course? Why does it matter? Mostly what we see physics being applied to in the world around us now, we're not looking at your typical force, your typical acceleration, that type of thing anymore. We really kind of understand that. So we're applying this knowledge now to technology. We're talking space travel. We're talking optics for cameras. We're talking magnetism. We're using these this foundational study of physics to apply to major technologies that we use in the world. So there are lots of different examples out there: electricity, cell phones, microwaves. I have seen a lot of advancement in technology in my lifetime. When I was in high school, we all had those like brick cell phones. I think I had one of the first flip phones and I thought I was cool. So, just saying, we've come a long way as far as technology is concerned. This part right here might seem a little confusing. The fact that we talk about physics being a basic science. And I think that physics isn't as complicated as people make it, because there are always fundamental rules that we have to follow as far as matter is concerned, as far as energy is concerned, forces are concerned. They will always follow basic rules because there's no other way that the universe works. If you drop something, it will always fall to the ground. Okay? So because we are just describing basic forces, what atoms are, what matter is, what energy is, how they interact with each other. It's actually incredibly simple because we just have to follow the laws of nature. It also relates to other sciences. I talked about how it relates to atom and matter. Well, chemistry is the study of atoms and matter and how those forces interact. So if we are going to increase our complexity, we can look at chemistry as just an example of physics. And then biology is overly complicated, right? Because there are lots of exceptions to the rules around us as far as like living matter. Like there are, to live, for you to live, you say, okay, well, you have to have oxygen. As an animal, you have to have oxygen, you have to eat, you have to have water. Well, there are some living organisms that exist out there that do not need oxygen. So there are always exceptions to the rule in biology that we wouldn't normally see in chemistry, and we would never see in physics. So how does physics kind of relate to all that? Well, physics or biology can go back to chemistry, that we're just molecules and cells that are interacting in complicated systems. So our most basic science of just how these interactions have to happen, we see can evolve through science and become more and more complex moving through chemistry and into biology. So physics really is the most simple of the sciences. But where do we start in physics? Well, the very most basic part of physics is going to be motion and forces, but we start with mostly motion. Okay, just movement. How do we move? And we're going to start with motion in one dimension and eventually motion in 2 and 3. So when we talk about 1D, that's just a straight line. Eventually, we'll move on to mechanics and how we can use forces to our advantage. Things like, how did the Egyptians build these massive structures? And while some of it is unknown, we do know that we can use some things like simple machines to help create less work for us by taking more force on an object. So obviously we've been studying physics for a really long time and using it, but the idea of putting that into a science really didn't happen until about 3,000 years after the Egyptians made pyramids. So it's been a long time. And everybody's favorite scientist and mathematician, Isaac Newton, is to blame for physics. He also created calculus and a couple other studies. So really, the idea was the application of this math system to the world around us, focusing on mechanics. Specifically, we're going to look at force and motion. And what you'll find is when we're talking about these type of motions and forces, everything has to be measured. So we will get into that a little bit in chapter 2 as we progress through this, along with our force and motion, because measuring is going to be incredibly important. Okay, it's the most fundamental part of physics, is being able to measure things. Eventually, we'll move into chapter 3, which is going to be position and velocity. We will talk a little bit about position more as we begin talking about displacement and distance here in the I believe we're going to start that tomorrow, or you're going to watch a video today and then do an activity tomorrow. So position indicates where you are in physical space versus velocity is going to look at speed and direction of where you are going in space. Chapter 4 will go into acceleration. This is change in velocity. Chapter 5 will do Newton, which is pretty typical of any introductory course. You know, Newton has 3 laws of motion. We'll get into all of those and how force plays a role in that. 3 and 5 will go into motions along a line. And then Chapter 6 will begin talking about motion in 2 dimensions. Okay, as you can see here, if you kick the ball straight, that would be a line. But if we created an arch here, you see we're starting to get into angles, which will be more like pre-calculus type of math, as opposed to just straight algebra. Eventually in chapter 7, we'll talk about circular motion. What we will focus more likely on is going to be the roller coaster part of physics. How do we create this circular motion? How can we force something to move in a complete rotation like that? It's a little more difficult than it sounds. This is important for things, not only roller coasters, which are fun, but it's practical knowledge for things like satellites. Which will, of course, lead us into a little bit of astronomy, not astrology, astronomy, talking about orbit, which obviously we've discussed satellites orbiting a planet, but how do planets orbit a sun? How do moons orbit a planet? Okay, so we're also going to talk about some of that in context of force in motion in a circular manner. Eventually, chapter 8 is going to be static, equilibrium, and torque. Equilibrium is just balance, and then torque is turning, or twisting, I should say. This is just kind of the quick overview. And then energy is typically where semester 2 will begin. Energy no longer focuses on matter. Energy is the state of not being matter. This is why kind of that division happens, is that we no longer have, or we'll get the basics down, then we'll move into more of energy and why that's important in physics. Which will lead us to work and energy. I'm just going to go through this very quickly. You do need energy to do work. We'll talk more about the physics definition of work and why it's important. Law of conservation of energy. Once again, a law. Universe states that we cannot create or destroy energy or matter, but energy cannot just disappear and go nowhere. It has to end up somewhere. It is just transformed into some other type of energy. So now I'd like you to take a second in which statement correctly describes the science of physics. Is it the study of living things, chemical bonds and processes, the study of medicines, or the study of matter and energy? If you did not select D, we have problems. Now you're going to take a second and go back to your initial answer to these questions, and we're going to make sure that they are correct. In order for a car to stop, its brakes must apply what to the wheels? Hopefully you put force. And energy is needed to do work, such as lifting a heavy mass. The next thing that you looked at yesterday was going to be waves, electricity, light, and the atom. Okay. We will eventually next week do this digital keyboard assignment, so don't freak out. That investigation will happen. I just want to talk through kind of what you've read and what you read about yesterday. Once again, you do have physics terms. If you have not written these down with their definitions in your notes, I would also write down this equation. I would do this on the inside of your notebook, so that way whenever you open it up, you have a list of equations. This will be our first one, where we're talking about frequency. We'll talk a little bit about more what this means here in a second. So we've talked about the mechanics part, where we're talking motion, energy, force, momentum, that whole shebang that I just went over. But there are other topics, and these are the ones that we will kind of get to play around with and choose what we want to do towards the end of the year. As there are, I believe, mostly seniors in this class, the end of the year I know is going to be very weird, and you guys will be done early. So it'll be a little bit of an odd end of the year, so I like to end it by selecting what we want to learn about. So I'm going to go through those all pretty quickly to get through that. We will probably do the oscillation and waves because it does tie into energy really, really well. But the rest of these we can kind of play around with. So be thinking about that as I talk about them a little. So oscillation is just a vibration back and forth. Think about if you've ever strummed a guitar, how that string goes back and forth. That is an oscillation. And they can be described in terms of their frequency. How often are they going back and forth? Okay, how long does it take them to complete that one whole back and forth? So if you were to play an A, we actually know the frequency at which it occurs. It would, for every 1 second, it would go back and forth 440 times, sorry. And then cycles per second actually is hertz, if you've ever heard that before, as a unit of measure. Chapter 15 describes waves and kind of how those oscillations move. All of these are an example of wavelength. We wouldn't see color if we didn't have any wavelength. We wouldn't have any radio. We wouldn't see ripples. We wouldn't be able to hear things. Sound waves obviously are waves and are just traveling oscillations. And then what these waves are doing is they're actually carrying energy with them and information in that energy that our brains then process as either light or sound or color or movement. Additionally, sound waves, for us, we can register that as any type of oscillating music would be an example. Additionally, we can use sound frequencies to produce an image. This is what an ultrasound is. Technology in the form of electricity. Technology in particular plays a major part in our modern physics. I want you to just kind of pause and jot down and answer these questions. What are some devices you use every day that would not be possible without electricity? And I want you to think beyond just your cell phone and your Chromebook. Okay, really think about all of the things that you use daily that require electricity. And I just want you to take a second and write all of those down. Electricity exists because matter has a property called charge, which we would talk about in chapter 18. What is a charge? How do we get a charge? And we'll kind of reflect back to chemistry on those protons and electrons. Of course, we do see it naturally. We see electricity in lightning, but you don't want to get struck by electricity. That would be horrible. By lightning, I should say, or electricity. Like I said, every time you get electrified, even a little bit electrocuted, you do damage to your heart. We could talk about magnetism, opposites poles attracting, and then like poles repel. So obviously, if you've ever played with magnets and you've tried to push two like ends together, they will push the magnets apart. So we discuss a little bit about like that and how it can create things like a compass, and how we can move electric charges with magnets, which is also interesting. Lights and optics would be another option. We can only see objects around us if they emit or reflect light. If they don't, we don't see them. That's why air looks invisible to us. While it is matter and it exists, it doesn't reflect light or emit any light, so we don't see that. Light will travel in straight lines. It is not a wavelength. And mirrors and lenses we can use to redirect light, and from that we can actually form different types of images. So optics and light we would be talking about in later chapters if we so chose. Matter and heat, we would be talking about thermodynamics here. You may have heard that term before. There are a couple laws that we would have to follow. And we would look at different states of matter and how temperature would affect those objects. In addition, we would talk about how we could harness heat to create things like engines to do work for us. We would talk about the structure of atoms, which we have always briefly covered in things like chemistry, or you may have learned about it all the way back in like 7th or 8th grade, talking about how elements are made up of atoms. Well, what do those atoms look like? How are they composed? So your basic protons, neutrons, electrons could be an option for us. Additionally, we would take it one step farther for us in that we would talk about quantum physics. So when we talk about quantum physics, we're looking at how the universe is going to behave because of what's happening at the atomic level. How is the structure of this atom creating the world around us, and interact in the ways that they can interact with each other. Finally, we could talk about nuclear physics. I said that weird, nuclear physics. What makes something nuclear? Okay, how can we harness that energy? What happens if something goes wrong with harnessing that energy? Things like, I do believe they briefly discuss the atomic bomb, which would also fit into that nuclear sort of physics category. But just kind of a fun fact for you is that 20% of our nation's electricity is actually generated by nuclear reactors. And we do have one close by in Clinton. So now for our kind of end of the lesson assessment, I want you to name 2 devices that you use today at some point and identify one of those aspects of physics that I talked about. Is it optics? Is it magnetism? Is it nuclear? Hopefully not, maybe, I don't know. That we're directly involved in how those technologies work. And then answer the question for me, which of these wave descriptors is related to the pitch of a sound wave that you might hear? Do you think that it has something to do with speed, frequency, amplitude, or all of the above? Hopefully you got this one right. Your answers will vary here because everybody used something different today. The one example that I wanted to share with you guys is if you've taken a picture, not only did we use electricity to charge our phone, to turn on the phone, whatever, but optics play a role in a camera. Capturing that picture and producing an image for us. So that was one option I wanted to share with you guys. This concludes our slideshow for today. Please begin the video on distance versus displacement.